Okay, so let's continue with the load store unit discussion. So basically what we consider so far, right, is that fetch is going to take one cycle. Accessing the data is going to be one cycle. But the thing is, fetching means that you go to the memory to get the data. Basically, this is your code that are in the memory. Accessing the data also take one cycle, right? You need to go to DRAM to get data, and that's not true. In reality, you take a lot more than one cycle, right? Memory actually take a long time to access, and it's limited, right? You have limited bandwidth. There's so much parallelism can you get out of the memory. So how do we handle that when you put out of order execution into the context? So the content in the memory has to be updated in the program order as well. If I have future store, it should know that the store will happen in the future. So if there are more load that come afterward, you need to check if that's going to impact the data I'm trying to load or store or not, right? Because there are dependency between your load and store instruction. And how do we detect this dependency, right? There are multiple strategies here, but the safest strategy is I will check for all the pending store and wait until they're done. And to do this, right, it means that for anything in my, basically in my instruction windows or what I need to have is, I want to be able to see what are my ongoing store operation. And if I have a load operation, am I depending on this store? Why is that the case? Load needs data. Store is updating the data for you, right? So when you have a load instruction, one thing we might want to assume is that the load are either dependent or independent, or we can just have some redirection somehow, right? Then we recorrect the course of action if we are guessing incorrectly. So one thing you can do is modern processor employ this unit called the load store queue. The way it works is I have two queues, and the queue will contain the information about load and store. And the obvious part is when I have a load instruction, I will search the store queue and see if it's actually having the data I want to load in the store queue. The less obvious part is when I have a store instruction coming in from the out of order dispatch, I want to also look at the load queue and see who need my data so that I can basically send forward the data to you. And you can also combine the two queues into one single queue, right? And this explanation sounds a little bit high level, so let's actually use an example, right? So the question is, to design the load store unit, right? We can perform out of order execution for the load store unit as well, right? When I have the store instruction, it only produce basically quote unquote, I produce new data based on the address I want to store, right? So in the memory point of view, store doesn't block the pipeline. I just write to DRAM, and if someone needs the data, I can forward it to you. Load is what blocks the pipeline because I want something into my register, and that register is gonna basically can be needed later. So if I want to go to DRAM to get something from my register, that might block the pipeline, okay? So if you have a load to some previous store and it just happened that that store is still in the store buffer, in that case, it can forward to you, right? So to actually get this, how do we implement in hardware? You want to get the type. First of all, are we loading or are we storing to the memory? Then what's the address of the load or store? And if I have the address, I want to also maintain the data associated with the load or store, right? And allow the pipeline to run in out of order mode. Load and store can be done independently of future instruction, except when there's data dependency. All right. And future instruction that needs data from these address can store and forward the data to a load, right? Here's an example. I have the load buffer and store buffer. Okay. Let's say I have load A to address A, load to address A, right? Coming in. Then I have the load to address B that comes in, right? So these are to address A and address B. And let's say I see the third one, let's say I want to load to address A, right? So the first thing you would notice is that, hey, I'm actually loading to the same, actually loading the same data from the same address, right? So first of all, you can combine the load so that when the request to DRAM comes back, I'll just dispatch it to whoever needs address A. Okay. Now let's say what happened right after is I want to store to address A. Now the address A will have new data. From this point on, if you want to load to address A, I would use the color red instead of color blue, right? So to specify that it's a two different piece of data. It's the same address, but the data is different. Now, let's say I have a new store coming in. I want to store the new data for B, right? In this case, also, let's say I keep fetching my program. The next thing I say that I want to load to A, right? I mean, obviously, these three have to go to DRAM, right? To DRAM to get your data, but I want to load address A, and now you see that, hey, I have a store to A. That's the red version of my store, right? It basically means that, well, I have the data for A. I have the red version. I haven't finished writing to DRAM, but here's your data, take it. So load to A in the future can now actually take the data from the store buffer, right? And the same thing, if you have a load to B, right? In this case, you can also forward the data, right, to the new load, the green version, right? But the two things, load A and B in the beginning, that has to go to DRAM. The third load to A, I mean, it can be coalesced or combined. And you don't have to issue two requests to A to get the blue version of A. But in this case, right, they can be combined. So to kind of wrap up this example in Thai, just to make sure everyone understand, alright ก็คือสมมุติเรามีโหลดเข้ามาแล้วแต่ละสีคือเวอร์ชันของแต่ตัวแล้ว A กับ B คือ address นะครับแล้วเรามาถึงเราต้องการโหลด address A ตามด้วยโหลด address B เราไม่มีทั้ง A กับ B เราต้องวิ่งไปที่ DRAM อันนี้ใช้เวลาอยู่แล้วก็คือใช้เวลาแล้วโหลดตัวที่3คือโหลดไป address A อีกรอบเนี่ยเพราะว่ามันเป็น address เดิมไอ้โหลด buffer เนี่ยมันก็จะ detect ว่าเอ้ยมีคนต้องการโหลด address นี้อันเดิมเลยมันก็จะ combine แล้วก็บอกว่าถ้า data กลับมาปั๊บก็จะแจกให้กับ register ที่เราต้องการโหลดเข้าไปนะฮะแต่ว่าพอเรามี store มาใหม่เป็น store ที่ address A เราต้องการอัปเดต data จาก data เป็น data prime อะไรเงี้ยคือสีแดงเป็น D prime ส่วนสีน้ำเงินเป็น D นะครับแล้วมีโหลดเข้ามาบอกว่าต้องการโหลด A อันเนี้ยเราสามารถส่ง D prime ไปที่โหลดตัวนั้นได้เลยแล้วก็ไม่ต้องวิ่งไปที่ DRAM นะครับก็เหมือนกันเรามี store มาที่ B เป็นเวอร์ชันสีเขียวเนี่ยโหลดในอนาคตที่เป็นเวอร์ชันสีเขียวก็จะสามารถถูก forward ไปได้เลยเหมือนกันจาก store buffer นะครับส่วนไอ้ข้างบนเนี่ยก็คือเสร็จเลยนะครับ so basically the benefit is you can kind of forward the data from the store buffer to the load buffer and vice versa. Like basically, if you have store coming in, right, and you have pending load, but it's done in the out of order manner, the new store might actually be the previous store, right? So let's say that's like the store to A and data, right? But it's for this guy, right? It's like the older instruction that got dependency and I can never dispatch until now. Now the blue version will have the new data being forwarded to the load as well. Okay. So for this particular example, we kind of skip over some advanced design issue, which include things like sometimes we don't know the address until you execute, right? Like I don't know where I'm loading from. I don't know the address. So this means that the rename, why is this the case, right? renaming for the address can be more difficult than just the typical data. You need to kind of perform partial execution to know that's the address I want to load, right? And sometimes this depends on other load store. So by the time you have the address, it's too long, right? So you have two choices. You can aggressively guess or you can wait. So these are some of the kind of like a research level design issue that you can explore, right? And younger load can have address ready before auto store. This is called memory disambiguation problems. And there are multiple ways to handle this. You can conservatively stall the load until all the previous store have the address back. You can aggressively say, hey, every single load is going to be independent from each other, from all the unknown store address, right? Again, this is the case where, for example, I have a load buffer here, right? Load, and I have a store, right? So I have load coming in, right? Load, load, and load here. I can also have a store here, right? But I don't know the address of the store because I'm still computing it, right? One thing that can happen is, well, we can assume every single thing has independent address and aggressively like keep loading. Or I can try to predict the dependency of the load. Like, are these dependent between each other? Can I forward the store from here to here, right? Because I don't know the address, that is something you have to kind of figure out. Again, this is like a design issue. You can be conservative, right? Wait until the previous store know the address. You can be aggressive and then redo if you're wrong, right? So if you want to, that's the first option is conservative. You wait until previous store committed. Now you know the address, so you can forward right away. Otherwise, you would kind of keep the pending store in store buffer and check if the load address match, right? And in terms of scheduling, if you assume dependent load, there's no recovery. It's going to slow you down because you assume that every single load might depend on previous store, all right? You can also assume independent loads. It means that I can issue the load right away. I can go to DRAM right away. But if I'm wrong, if the address is not what I assume for the previous store, I need to do some recovery because store is going to update my data. So I need to recover from that. I can also predict the dependency status of a load on any outstanding store is more accurate. And still, if you mispredict, you still require recovery, but hopefully this is better. All right, and this is the design choice that can impact performance. And also modern processor, because you have this load and store buffer, you can say that there are multiple active load and store in the buffer, which means that you're gonna issue all this data access in parallel, right? As long as instructions have the data that can be executed, it also means I can issue parallel access to DRAM. This is why DRAM bandwidth is so important for many parallel execution, including your code on the GPU. You want a lot of bandwidth because it's gonna basically go to DRAM all the time, and that's gonna be parallel DRAM accesses. So that's it for the class today. Before we leave today, basically we have a midterm in 2 weeks. All right, we will continue with the lecture. The material next week will be for your final, not for your midterm. All right, the midterm is basically anything up to today. And the format is going to be, as we discussed, change from 3 hours to 6 hours. I will be here, right? I'll be online for 3 hours in the beginning, right? And then you have 3 hours to yourself to keep working on it. And then the canvas gonna open up the midterm, then close after 6 hours. It's online, open everything, all right? I would assume that 6 hours definitely too short to actually explore too much and get a lot of help, but it's long enough so they can kind of work on the problem, okay? Make sure you know the basic material, and if you have any questions, please let me know, but definitely please go through your sample exam and come with question next week if you have any question from the sample exam, okay? So from the lecture point of view, that's basically it for the lecture. All right. I want to basically stop the recording now so we can cut to like a Q&A. And if you have any questions, and we will basically talk a little bit about the first review that you guys are doing. How do you think? How do you like it? Okay.